We have a lot to learn. So I want to start by just doing a quick review because we're going to have to fly through some of this stuff. So just a quick review of the very last thing we did yesterday. Oh, by the way, there's a correction in the 6.2 homework. I said 6.2, it's 9.2. 9.2 homework. So you might want to make that correction. Now, yesterday, the last thing that we did was expand this. So you might recall, since it was just yesterday, that I worked out like x plus y the first and x plus y the second. I worked all those out. And then you made some observations about what x plus y to the fifth would be, right? And the variables and exponents, there's a very definite pattern to those. But if those coefficients on the expansion were a little bit weird. So does anybody remember how we generated the coefficients for each of the terms in this expansion? A couple of different ways, Sam?
Pascal's triangle.
So we can use Pascal's triangle, which looks like this. And since we're expanding to the fifth power, we would need the fifth row of the triangle. And say, okay, so 1, 1, and then we add, to get the middle terms of the triangle, you just add the two that came above it, right? Who remembers the other way we had, though? This is fine. I use this all the time if I'm expanding to a relatively low power. But I think you can see if that were a 20, this would be kind of a hassle because building this out to the 20th row, are you following what I'm saying, would be awful. Okay, so what other option did we have?
You do the combination.
The combination. So in the fifth row of Pascal's triangle, the numbers in the fifth row of the triangle are the 5C numbers, the combination numbers for 5. So 5C5, 5C4, 5C3, and so on, and the last one's 5C0. So if you wanted the numbers in the 20th row of the triangle, the first number in the 20th row, or the first coefficient of the expansion to the 20th power, would be 20C20, and then 20C19, and so on down the line. So, just to refresh from what we did yesterday, to expand this without literally foiling it, because you could foil it, but that would take forever, you can just write down the coefficients from the fifth row or the 5C numbers, and then next to each of these is going to be an x and a y, because those are the two parts of your expansion, x, y. And then the powers on the x and the y are very predictable. If you FOIL this out 5 times, x plus y, x plus y, x plus y, doesn't it make sense that the highest power of x you would have would be 5? And then they decrease from there. We observed that yesterday. This is what always happens. And then what about the y's? Same thing from the other direction. Because another observation we made yesterday was that each term, the powers add up to whatever power you're expanding to. Right? So then when you start cleaning this up, put plus signs between each term to separate them. When you start cleaning it up, this is just x to the fifth. This is 5x to the fourth y. 10x cubed y squared, 10x squared y cubed, 5xy to the fourth, and that's just 1, so y to the fifth. Is that what we got yesterday, I hope? All right, so that's a recap. So now we're ready to do the next problem that says expand 2x minus y to the fourth power. Okay? We just increased our group by 25%. Good job. Now, I do not want to FOIL this out 4 times. I could, and it would give me the right answer, but I don't want to do that. So let's repeat this process for that problem. All right, so here we go. I'll take the coefficients from the 4th row of the triangle. So 1, 4, 6, 4, 1. Everybody's clear on that? We don't have a lot of time for a bunch of examples. So we're going to take the 4th row of the triangle. Next to each of those coefficients, I'm going to put a 2x and a negative y. Now this is not a subtraction. I am multiplying a multiplicity power of 2x times a power of negative y. So 2x and negative y are the 2 factors that comprise my binomial. All right, so in our previous work, we had just an x and a y. But now we're making it a little tougher. Now we have a 2x and a negative y. Now let's put the powers on. So we know that if we're expanding to the 4th, the first power on my x term will be 4, and then counts down. And then the y's do the same thing from the other direction. Now, each of these groupings here is a term. So I'm going to separate them with plus signs to keep them separate. And then I have to simplify each term. So the biggest mistake that's made in this, because this is an easy process, but the biggest mistake that's made is right here. Kids will say 2x to the 4th. Nope, it's not 2x to the 4th, it is 16x to the 4th. Notice when I built my expansion, I put each of these in parentheses. That is important because whatever power you put on there is going to the 2x or the negative y. All right, so what have I got here? Well, this one's going to be negative. It's going to be a negative term. And it's going to be 8 times 4, 32. X cubed y. Are you following what's happening here, guys?
Yep.
All right, now the next one's going to be positive. Would you agree? Be positive. And it's going to be 24 x squared y squared. The next one will be negative 8 xy cubed, and the last one will be positive y to the 4th. Changing the problem does nothing but change the numbers. The process is exactly the same. Get your coefficients from this row of the triangle, or from the combination numbers, 4C4, 4C3, and so on. Each coefficient gets matched up with a power of this and a power of this, whatever they are. Put your exponents on and simplify. Okay? Now, the next problem in the notes doesn't want me to do the whole expansion. This is what we call the expanded, the binomial. Okay, we got the whole thing. The next problem doesn't want me to do that. The next problem just wants me to find a particular term. So, like these guys are terms. So if I wanted the second term, it would be right here. We want the 4th term of 2x minus 3y to the 6th. Now, if you were expanding the whole thing, you would go to the 6th row of Pascal's triangle, or you would use the 6C numbers, right? And then next to each of those numbers, you write out all the numbers, and next to each of them, you'd have a 2x and a negative 3y, and then you put the powers on. I don't want all of it. I want the 4th term. So I'm just going to count on my fingers. in terms of the coefficients, I erased my triangle, so I don't have those numbers anymore. So I'm going to use the C numbers. So the first term would be 6C6, 6C5, 4, 3. So the fourth term, the coefficient, is 6C3, which I can get from my calculator. Next to that coefficient, whatever that number is, there will be a 2x and a negative 3y. Just like here, this time it's a 2x and a negative 3y. Now again, I'm going to count, because I know if I have the whole thing written out, the first power on my x part would be 6. So 6, 5, 4, 3. So that power is going to be a 3. And then if that one's a 3, so is this one, because they got to add up to 6. And now I just simplify. That would be the fourth term. So I need 6C3, which is 20. This term, be careful, will be 8x cubed. This term will be negative 27y cubed. Are you still with me? Keep in mind, that's all multiplied. It's not a subtraction. It's all multiplied. So 20 times 8 times negative 27. So negative 4320 x cubed y cubed is the fourth term of that whole expansion. All right? So quickly, let's do the next one because it's a huge expansion. X plus 2y to the 20th. And for some reason, we want the third term of this. So even if you're a Pascal triangle fan, which I am, there's no way I'm doing it with this problem. So what do I need for my coefficient? I need the third term. So 20C 20, 20C 19, 18. So 20C 18, and then an x and a 2y. And would the power on the x also be 18? 20, 19, 18. And then that makes this one a 2. So I have 190 x to the 18th 4y squared. Did you get 760 x to the 18th y squared?
Yep.
Okay. Now, this is going to tie in, you're going to see, maybe today, you're going to see how this fits in with some really cool probabilities. This whole idea really fits. I got a couple other things to do first. All right, everybody keeping up? We're going kind of fast here because we have a lot of math to do. And you have the perfect opportunity to stop and ask questions since there's 5 of you. All right, find a counter example for this. Now, I told you yesterday, or the day before sometime, that factorials don't cancel. You don't do stuff with factorials that you can do with regular numbers. So basically, your job is to find a counter example to this. This is not true. This is not true. Okay? Factorial is not distributive, in other words. So come up with a counter example. Now, a counter example is nothing except plug some numbers in and show that it doesn't work. So I don't know, what numbers do you want to use?
2 and 3.
2 and 3. So 2 plus 3 factorial would be 5 factorial, which is 120, I think. Now, we're showing that that is not equal to 2 factorial plus 3 factorial. Because what's 2 factorial? 2. What's 3 factorial? 6. And clearly 120 does not equal 8. When you're dealing with factorials, it is, never try to shortcut. Just work it all out. All right, the next one now, we are actually going to prove it is true. So we're proving, oh look, we're back up to 20 more percent, awesome. Okay. So now we're gonna prove this. It looks very scary, but I need to clarify a couple of things first of all. This notation, did we talk about this? This notation? This parenthesis notation? This is another notation for combinations. So this, when you see this like parentheses written vertically like that, that's combination of n things taken r at a time. Combinations are used so much in mathematics that this is like the notation that's used because it's less writing than with all the C's. So this means this. So what we're doing is proving a concept that we talked about yesterday. We talked about this yesterday. Who remembers the formula? What does this look like in terms of our setup for calculating it out? Who remembers? Look in your notes. Wrote it down. Who?
N factorial over n minus r factorial minus r factorial.
Exactly. Remember, in terms of numbers, when we did, 20C18, in terms of numbers, that was 20 factorial over 2 factorial, 18 factorial. You probably should know that. That's kind of a biggie. So that's what that means. So, what does this one mean then? Well, it would be n factorial also. And then you gotta subtract these, right? So n minus r, and then n minus r. Okay, lots of letters going on. Remember, when you do a combination, it's that number, then you subtract these two, and then that number. Well, what happens, what's this? N minus n plus r? Isn't that just r factorial then? So this is n factorial over r factorial, n minus r factorial. Aren't those the same thing? So this is what I talked about yesterday. If you have 10C8, that's going to equal 10C2 every time. It's the symmetry of that triangle. Because if you choose 8 of the 10, you're automatically not choosing the other 2. So you just proved it with letters. All right, for the rest of the year, I'm just going to be skipping some stuff because we don't have time to do everything. So I am skipping to number 8 now. We're going to find the coefficient of the x to the 7th term. Now, first of all, would you agree that if I multiplied this thing all the way out, that somewhere along the line there would be an x to the 7th? Because it's going to start with x to the 11th. So it's going to start with the 11. 10, 9, 8, 7. I'm not looking for the 5th term. Just counting on my fingers, right? So I'm really looking for the 5th term. So what will the coefficient be on the 5th term of the expansion? Well, on the 1st term of the expansion, it's 11C11, 11C10, 9, 8, 7. The coefficient, 11C7. And then I'll have an x to the 7th and a negative 3 to the 4th. So 11C7 is 330, x to the 7th and 81. So that term is 26,730, x to the 7th. Did I do that too fast? Would everybody agree with that? So the question was, find the coefficient. The answer is 26,730. Okay. All right, so we're going to make our correction to the 9.2 homework. And then that assignment will be due Thursday. And we have office hours tomorrow, so I know I went through it pretty fast, so you take a look at that tonight. And if there's something you're not sure about, get in here tomorrow morning and we'll work through it, okay? All right, so now we're gonna talk a little bit about probability. Anybody know what a sample space is? When somebody talks about a sample space, anybody know what that is? It's about all the possible outcomes, okay? So a simple example to talk about is if I roll 2 dice, what is the sample space of sums? If I roll 2 dice, what is the sample space of sums? In other words, what are the possible sums? Sums. 2 through 12, right? So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 would be the sample space. All of the outcomes are either, when you roll 2 dice, the sum is either going to be 2 to 12. That's it. That's your sample space. All the possible outcomes. So many situations have huge sample spaces, right? But that's one that's reasonable we can talk about. All right, probability and odds. The words mean different things to the mathematician. When we talk about mathematical probability, mathematical odds, that's a little bit different than the odds at the racetrack. Okay, we're talking about mathematical probability and mathematical odds. Anybody know what probability is? The definition of probability? The number of successful outcomes over the number of total outcomes. So really quick, look over at problem number 1. We'll come back and talk about odds in a minute, but look over at problem number 1. What is the probability of tossing a head on one, toss a coin? What's the probability of getting heads?
50%.
Well, 1/2. I'll think of it as a fraction. 50% is absolutely correct. But I'll think about it as 1/2 because when I toss a coin, how many sides are heads? What I want, 1. But how many total sides are there? 2. That's what the definition means. What you want over total. So the next one. Toss 2 heads in a row on 2 tosses of a fair coin. Well, the first toss is going to be 1/2, right? What's the second toss probability going to be? 1/2. And since it's head and head, we multiply 1/4. Now, let's look at a sample space. If you flip 2 coins, what can happen? You can get 2 heads, right? You can get a head and a tail, or a tail and a head, or you can get 2 tails. So how many outcomes are there total? 4. How many are what you want? 1. By the way, that's the second row of Pascal's triangle. If you toss 3 coins, it would be the 3rd row and so on. All right, drawing the queen from a standard deck of 52 cards. What's the probability of drawing a queen from a standard deck? 1/13, which started out as 4 52s. There's 4 queens, 52 cards total, so that's 1/13. We always reduce if we can. Rolling a sum of 4 if you roll 2 dice. Okay, so think about that for a second. These I always kind of have to write out. How can I get a 4? I can get a 1 and a 3.
3 and a 1 and a 2.
A 3 and a 1, or a 2 and a 2, is that it?
Yeah.
So there's 3 ways that I can get what I want. How many total ways are there for 2 dice to land? Like if I wrote out all the possibilities, how many total ways would there be?
6 factorial.
Now, there's 11 total sums, but those sums can happen more than one way. So there's more than 11 possible outcomes. 6 factorial is a little bit too big, but you're on the right track. When I roll that first die, how many ways can it land? 6. Now I'm going to roll the second one. How many ways can it land? So if I roll the first one and the second one, how many total ways can they land? 36. There are 36 total ways. So what, we have 3 over 36 or 112. So Philip, do you understand what I said to you? Okay, because this represents one outcome, getting a 4. But there's 3 ways that can happen. So there are multiple ways you can get all the outcomes. All right. Guessing all 6 numbers in a state lottery that requires you to pick 6 numbers between 1 and 46 inclusive. Now, we talked about this yesterday. We just got to pick the 6 numbers. They don't have to be in any particular order. We just have to pick the correct 6. Okay? So what's your thought on that? The probability is not very good. Sam?
Would be 1 over 46, 1 over 46, 1 over 46, or 1 over 46 to the 6th power.
Okay, that's a great guess. First, it's 1 over, because there is only one combination of numbers that's acceptable. Would you agree with that? So, another way of thinking of that 1 is 6C6. There are 6 correct numbers, and you have to pick all 6 of them. It's like picking diamonds. If I said you had to have all diamonds, wouldn't you just have the diamonds here? 13? Well, these are the correct numbers, and I gotta pick all 6 of them. Now, how many numbers are there to choose from altogether? 46. And we're choosing 6 of them? That is the answer. Sam, you can't have multiple numbers, so you can't pick 7 twice. So it wouldn't be 46, 46, 46, and it won't even be 46, 45, 44, because order doesn't matter. And when you say 46, 45, 44, you are automatically putting things in order. So your way to approach this is with a combination. There are 46 possible numbers for you to pick, and you're going to pick 6 of them. That's the total. So that is a very low number. That is a not very good probability. Max is going to figure it out for us.
It's almost 1.
It's what?
It's like almost 1 in 10 million.
1 in 10 million.
Close.
That's higher than I thought,
It's like
actually.
1.93.
Yeah, 9366681.
Times 10 to the,
That was the number.
oh, okay.
It's like 9.30.
All right. Oh, that's the denominator.
Yeah, that's the
Yeah. So 1 over that's going to be small. Yeah. Okay. Now back to our definition. Probability is success over total. Odds are success, the number of successes, to the number of failures. And odds are often written sideways with a colon instead of a fraction. That's one way we kind of keep straight which is which. So when you said to me that the probability of rolling ahead, if I toss a coin 1 time, the probability of getting ahead, you said was 1/2. So the odds of getting ahead would be 1 to 1, because there's one head and one tail. These are called even odds. When your odds are even, it means you have as much chance of winning as you do of losing. So let's go back to our, oh shoot, we didn't really get any like that. Let's say, what's the probability, if you roll a die, what's the probability of getting a number greater than 4? Shoot, that's going to reduce. I don't want this not going to reduce. What's the probability of getting a number greater than 5? If I roll a die, what's the probability of getting a number greater than 5? 1/6. So what are the corresponding odds of that event? If the probability is 1/6, then the odds would be 1 to 5. Because if your successes is 1 way, and there's 6 total, then aren't there 5 unsuccesses? So that would be 1 to 5. So you can convert back and forth very readily. Okay? All right. A probability distribution, that just is like a chart. I've just given you an example of one there. It's just a chart that shows all of the outcomes and the probability of each outcome. Okay? So if I roll 2 die, the probability of getting a 4 is 3 out of 36. That says that in the chart. We figured it out, it says it in the chart. The probability of getting an 8 is 5 out of 36, and so on. That's all the probability distribution is. All right. Now, which we're going to use here for problem number 2 on the next page. Take a look at those facts about probability. I think you know them all already, but just take a look at them sometime. All right, find the probability of rolling a sum divisible by 3 on a single roll of 2 fair dice. Okay, so let's look at our probability chart, distribution chart there. I want to roll a sum divisible by 3. Okay, so what are the sums that are divisible by 3? 3, 6, 9, or 12, right? So my chart says 236, 536, 436, and 136. Now, if I didn't have this distribution already done, I would have to figure it out, just like we figured out the sum of 4 a little bit ago, right? It's nice to have the chart already done. Notice I didn't reduce these when I put them in the chart, because what am I going to be doing if I have to get a 3 or a 6 or a 9 or a 12? What am I going to be doing with these numbers? Adding them up. And it's a whole lot easier to add them when they all have the same denominator. So that would be 7, 8, 12. Is that 1/3?
Yep.
So the sum would be 1/3, the probability. Are you keeping up, guys? All right, we're rolling number 4. Remember, I'm skipping some stuff.
Oh, wait, no. Sorry.
All right, number 4. Sal opens a dozen chocolate creams and generously offers 2 of them to Val. Val likes vanilla the best, but all the chocolates look alike. If 4 of the 12 are vanilla, what is the probability that both of Val's picks turn out to be vanilla? Okay, so you've done that before. Somebody's given you a box of chocolates, and they all look the same, right? So it's like Russian roulette, right? You pick Russian roulette. All right, so here we go. What do you think?
Is it 4 12s times 3 12s?
Actually, since both of them are the same, I think that will work. Philip, actually, no, that wouldn't be quite right, but you're on the right. I think you can do the problem that way since they're both the same. I'd rather you got in the habit, though, of using combinations, because since they're both the same, I can do it in a permutation style problem, but I don't really care what order I get these. And if I had one chocolate and one vanilla, or one, whatever the strawberry flavors are, if I had one of each, then I would have to consider both orders if I did it the way you did it. So I don't want to do that. I don't want order to be part of this problem at all. So I'd like you to think about, here's how many are in there? A dozen. So there's 12 in there. So think, here's 12 pieces of candy. I'm going to reach in and grab 2. That's 12C2. The total number of ways that I can pick 2 candies, it's just like a card problem. Only now I only have 12 to choose from. If this were cards, I'd have 52. Now, that's the total number of ways that I can pick 2 candy out of 12. But what do I want? Think of your numerator. What do you want? You want them both to be vanilla. How many total are vanilla? 4. So you want to pick just from those 4. Does that make sense to you? It is the same situation as the card problems we talked about the other day. If I said to you, what's the probability of choosing 5 cards and all diamonds? Wouldn't your denominator be 52C5 because that's the total number of ways I can pick 5 cards? But what would your numerator be? If you want them all to be diamonds, then your numerator would be 13C5. This is exactly the same. This is the exact same situation. All right, so you can type that in on your calculator exactly as it is. You do not have to do it in steps. You can if you want, but your calculator will handle 4C2 divided by 12C2. And sometimes I like to change them into fractions. I got 1/11. Did you? Caution, sometimes they won't change into fractions depending on the size of the number, especially with these card numbers. That's such a big number. So if it doesn't, then a decimal is fine. But if it does change into a fraction, that would be a more accurate way of answering the question. Okay, so we're gonna, especially since I'm throwing so much at you all at once, remember, when you have a group of something and you're choosing from it, try to set your problem up as either a P or a C. And almost always in probability, it's going to be a C, because when we're choosing cards or choosing candy or choosing people for a committee, normally order doesn't matter. But try to think of it in terms of P's and C's when you are picking from a group, okay? Now, this next problem is different. Sometimes when we do probability, it's more convenient to do a Venn diagram. So we got the big headline, use a Venn diagram. 54% of the students are girls and 62% of the students play sports. Half the girls at the school play sports. What percentage of the students who play sports are boys? If a student is chosen at random, what is the probability that it is a boy who does not play sports? Oh my goodness. All right, so here's our Venn diagram.
I'm just confused with the square, to be honest with you.
What?
I'm just confused with the square, to be honest with you. That's-
Confuse it to square.
I was
Oh,
yeah.
normally when we do a Venn
Yeah.
diagram, we draw this is called the universal set, and then we put our smaller sets in there. If you don't wanna do that in this problem, you don't have to, because, well, I don't know how you're setting up your circles. What are your circles?
Well, I'm just saying, I was like, that's why I was looking.
Yeah,
Like,
normally
it doesn't matter.
so the box contains all the students in the school.
Yeah, it's like that.
Okay, and then the circles are in there, dividing it up into different sections, okay. So, what's your thought on this, Max?
I do the box of students and then divide the box in half, roughly 54%.
Like that?
Yeah,
Okay.
54% of it is girls and 46% of it is boys.
Okay, so if we don't want to, use percents, could we say there are 100 kids in the box? If you'd rather use whole numbers, it doesn't really matter. And here, this is the box of girls, and there's 54 in this box. And this is the box of boys, and then I guess there would be 46 in that one? All right, then what? So that's certainly a picture of the situation. Now we gotta throw in, the whole sports thing. What do you think about that?
Draw a horizontal line, and then one of the bits is gonna be 62% of it.
So we draw a horizontal line.
Like, in one of the, either the top or the bottom, whichever one.
Could we draw a circle like this and say these are the sports kids? Because some of the girls are sports and some of the boys are sports. Okay, and we know that the total in the circle, is 62 kids. But we also know that the girl side of the circle is 27. Are you following? So what is the boy side of the circle? Since we know the whole thing is 62, the boy side must be 35. What percentage of the students who play sports are boys? Now be careful, not 35, because what's 35 again? 35 is the number of boys who play sports. So how many kids in the school play sports? 62. So the answer to A would be 35 62s, wouldn't it? So 56.5%. If a student is chosen at random, what is the probability that it is a boy who does not play sports? So in other words, reach in the box and grab a kid. What's the probability you'll get one that's a boy who doesn't play sports? Well, I got 100 kids to pick from. How many of them are boys that don't play sports? 11. So 11%, or 0.11. You can write your probability however you want, decimal or percent. That's kind of a weird looking Venn diagram. But the idea of a Venn diagram is to show how sets compare to each other and how they overlap. So the boys and the girls don't overlap, so that's why Max said let's just split it right in half. But the sports do overlap. That's interesting, good idea. All right, use a tree diagram. All right, Now we're gonna try a tree diagram. Two identical cookie jars are on the counter. Jar A contains 2 chocolate chip and 2 peanut butter cookies, while jar B contains 1 chocolate chip cookie. We select a cookie at random. What is the probability that it is a chocolate chip cookie? Okay, so you walk into the room, all right? And there's 2 cookie jars here, and I say, have a cookie. All right, what's the first thing you have to do? You have to decide if you're gonna take it out of the blue jar or the red jar. So, we have jar 1, did they name them? A. So jar A and jar B, so that's your first decision. What's the probability you'll choose jar A? 50%, 1/2. And jar B, 1/2. You just come in, you're gonna have to pick a jar. Now, if you pick, once you pick your jar, then you're gonna reach in and get a cookie, and it's either gonna be a chocolate chip cookie, or it's going to be a peanut butter cookie. Now, if you happen to pick jar A, what's the probability that you will reach in and grab a chocolate chip cookie? 1/2. I'm gonna go ahead and write 2/4, just so we remember how we got that 1/2. There were 4 cookies in the jar, and 2 of them are chocolate chip, and the other 2 are peanut butter. It is 1/2. You're right, it is 1/2. And then what if you pick jar B? There's only 1 cookie in that jar, right? So the chances of you getting a peanut butter, 0. There aren't any peanut butter cookies in that jar. So now we want the probability that you picked a chocolate chip cookie. Well, if you go to jar A and pick a chocolate chip, won't that be 1/2 times 1/2 or 1/4? But if you go to jar B, it's 1/2 times 1, which is 1/2. So your probability of getting a chocolate chip is 1/4 out of jar A or 1/2 out of jar B. So what do we do with those 2? Add them. You have a 3/4 probability. Is that making sense? All right, then let's look at the next question. Given that I picked a chocolate chip cookie, what is the probability it came from jar A? Okay, so I'm standing out in the hallway, I send you in, I say, get a cookie. So you get a cookie and you walk out. I said, what kind of cookie did you get? I got chocolate chip. All right, what's the probability? I'm trying to figure out what jar it came from. Okay, did he get it out of jar A or jar B? How am I gonna do that? What's the probability that that cookie you got actually came out of jar A? Well, this is called conditional probability because we're talking about what's the probability it was chocolate chip, or what's the probability it came out of jar A given it was chocolate chip. There's a formula for that. I wrote it down for you, I think, or cut it out and pasted it there. The probability of B given A. So the probability it came out of jar A, given that it's chocolate chip, is calculated by taking the probability of both over the probability of whatever was given. This is the intersect symbol, that means and. So let's look back at our tree diagram. This is really easy. The A and B part's confusing. This is, for us, what's the probability it came from jar A, given it was chocolate chip? So, jar A and chocolate chip. Isn't that right here? Isn't it that right there? So 1/4 is my numerator. And then the denominator is the total probability of chocolate chip, which you have figured out already was 3/4. The probability you get a chocolate chip cookie is 3/4. So what's the answer to the question? 1/3. So the probability of that it came out of jar A, given it was chocolate chip, here's your formula every time. Probability of both over the given, the second one, the given one. This means the probability of B given A. All right, let's try number 7. As of the year 2003, the probability of an adult having HIV/AIDS was 0.006. Test is used if the antibody is present, the test reports positive, and negative if the antibody is not present, the test reports positive and negative. All right. So we could actually, change this to COVID. They got numbers like this for COVID too, I'm sure. So here's the deal. You either have the antibody or you don't have the antibody, right? So let's say have it, don't have it. They give you a test. You're either going to test positive or negative. Would you agree that's true? All right. So what's the probability that I actually have the antibody? Tells you in the problem. Exactly. So I have the antibody 0.006. Not having the antibody then would be 0.994. Remember, you either have it or you don't. There's no other option. So these have to add up to 1. Now, if I have the antibody, the test reports positive 0.997. Which means negative would be 0.003. Keep an eye on my subtraction. Would you agree? Oh, it says that. It actually gives it to me. If the antibody is not present, so no antibody, 0.015, this is called a false positive, right? You don't have it, but they're telling you you do. And then this would be 0.985. They actually don't have to give me these two numbers. You should be able to figure those out, but they gave them to us, so that's good. Are we okay with that? Okay. Use the conditional probability formula to find the probability that a person with a positive result actually has the antibody. So in other words, given we're positive, what's the probability that we're actually sick? That we actually have it, that's true. Okay, so let's find the total positives. So the total positive probability would be 0.006 times 0.997. This is, I'll say sick and not sick. This is antibodies, I'm sick, I really am sick, and I'm positive. That's 0.005982. Now, I could also test positive if I'm not sick. And that would be, oops, 0.01491. Are you still with me? So I am finding the total probability of me being positive. The total probability of me being positive is those two added together. So the probability of being positive is 0.020892 if I typed it in right. So if the question said, what's the probability you will test positive? That's it. I test positive here, or I test positive here. So antibody and positive, no antibody and positive. So the total would be those two added together. Agreed? But the question isn't, what's the probability I'll test positive? The question is, what's the probability that I have the antibody given I tested positive? So in other words, I go in, I have this test, it tells me I'm positive. What's the probability I'm really sick? Well, our formula says this would be the probability of having the antibody and being positive over the probability of being positive, right? So I just figured out my denominator is 0.020892. What's my numerator? My numerator is the probability of having the antibody and positive. Isn't that this big number right here? That's right here. So that's my numerator. Did you get 0.286? What does that mean now? What does that mean? That if I go in and get this test, and I test positive, there's only a 28% chance that I'm really sick? It's a little scary. Right? That would not be a very reliable test. Okay. I'm going to do one more problem and then I'm going to stop because you're going to go into overload here if we're not careful. But we're going to tie together everything we talked about today. So this last problem is the perfect one to do that. It says we roll a die 4 times. So we're going to roll a die 4 times. What's the probability we roll all 3s? Now, I want you, okay, this particular one's easy. These problems can get a little more complicated, so I want you to kind of open your mind and think about something for a second. When you roll a die, there are 2 outcomes. You're either going to get a 3 or you're not going to get a 3. Right? In this problem, I only care about 3s. So I don't care about all the other things. I'm either going to get a 3 or I'm not going to get a 3. Right? And the probability of me getting a 3 is 1/6. And the probability of me not getting a 3 is 5/6. Would you agree with that? Now, I'm going to roll this die 4 times. And I want every single one of them to be a 3. So in other words, if I have 4 rolls, I want all 4 of them to be threes. There's only one way that can happen. 3, 3, 3, 3, that's it. But if I were getting 2 3s, it would be 4C2. This is how many options I have, how many rules I have. This is how many I want that, of what I want, which in this case is 3s. If they're all 3s, then the power on the first part, my first probability, is going to be 4. Because that's the free probability, and I want 4 of those. I don't want any of these. 0 of those. I want every one of my rules to be a 4. Or 3, I mean. All 4 to be 3s. Does that look at all familiar to anything else we did this morning? It's binomial expansion. This is called binomial probability because there's only 2 outcomes. You're saying, but this 4, you can get a 5. No, we're not talking about that. In this problem, we're getting a 3 or we're getting something else. Those are the only 2 outcomes. So we can set it up exactly the way we did our binomial expansions. This is your coefficient. 4 rolls of the die means 4th row of the triangle. Instead of x's and y's, you've got your 2 probabilities, and you take them to whatever the desired power is. So that would be the answer to the question. Well, what if we wanted no 3s? Well, the setup, the basic setup is going to be the same. You're still going to have the same probabilities. But if we want no 3s, then we need 4C0, no 3s. No 3s and 4 other things. Exactly 2 3s. Exactly 2 3s. What does that look like? 4C2, 1/6 and 5/6, and what will be the powers? 2 and 2. You can do this with anything that's binomial. So think about a multiple choice test. Let's say there are 10 questions, and they have 4 options, A, B, C, D. It's a multiple choice test. And you're guessing. What's the probability that you will guess exactly 9 right? Well, not very good, but how would we calculate that? 10C9. What's the probability? If there's A, B, C, D, 1/4, 9 of those, and 3/4, I want 1 of those, because the probability of getting it right is 1/4, and the probability of getting it wrong is 3/4. Right? My stepmother, one of 10 children, only one's a boy. That fascinates me. So, Coach Kesterson, who retired a little bit ago, Jean Kesterson, volleyball, same thing in her family. There's 10 kids, 9 of them are girls, 1 of them's a boy. So, what's the probability of that happening? Well, 10C9. 1/2 to the 9th and 1/2 to the 1st. Would you agree? That's the probability that you would have 10 kids, assuming that it's 1/2, 1/2. And I know it's not exactly that, but just for argument's sake, it's close to that. So that's a little tiny number. The probability is not very good. Anyhow, that's enough for the day. You guys have been magnificent. And we have packed in a lot of cool stuff.